Hello, my name is Jean and I am a junior physics major at Yale University. Today I will be presenting my work on the operational and data analysis improvements for a quantum-enhanced search for dark matter axions. This project is a part of the Phase 2 dark matter axion experiment with the Haystack collaboration. The axion is a well-motivated cold dark matter candidate. It was first postulated in the Pessi-Quinn solution to the strong CP problem in quantum chromodynamics. The axions can be converted to photons in the presence of electromagnetic fields. Haystack makes use of a tunable high Q factor microwave cavity, which is embedded in a strong static magnetic field at cryogenic temperature. The cavity is then coupled to a low noise readout system. The axion signal is resonantly enhanced when the frequency corresponding to the axion mass falls within the bandwidth of the predominant cavity mode. Since the axion signal power is theoretically predicted to be very low, experimental searches for axions have always been limited by quantum uncertainty. In the most recent experimental run at Haystack, we utilized vacuum squeezing technology using two flux pump Josephson parametric amplifier and achieved sensitivity beyond the standard quantum limit. The reduction of quantum noise increases the signal-to-noise ratio, which leads to significant runtime enhancement at each frequency step. A schematic of the microwave setup can be found in Figure 2. The experimental setup builds on the previous Haystack run, when the quantum limit has not yet been reached. I will be focusing on a selection of operational and data analysis upgrades, which were then used in the actual Phase 2 experimental run. The optimization of JPA squeezing requires precise in situ measurements of the cavity transmission and reflection profiles. The complex transmission and reflection coefficient spectra are taken using a coaxial antenna built in the microwave cavity. The real cavity measurements can be affected by experimental imperfection, such as the difference in spatial positions between the coupling port and the plane of measurement. As a result, the transmission and reflection profiles are pre-processed with a correction function to account for these imperfections before being analyzed using the least square fitting to an asymmetrical Lorentzian curve, from where we can obtain the resonance, Q factor, and coupling parameters of the cavity. Figure 3 shows an example of such a measurement, which is then automated at each tuning step during the actual experimental run. In addition, the system loss measurement is essential in determining the system noise temperature and calculating the signal-to-noise ratio. The losses in transmission lines between the two JPAs can be modeled as a replacement of a fraction of the signal with the Johnson-Nyquist noise at the temperature of the dilution refrigerator. Figure 4 shows an ex situ measurement of the transmissivity between the two JPAs. On the data analysis side, the runtime of our data analysis programs has been significantly reduced by parallelized data analysis of subspectra at each cavity tuning step, and the analysis procedure has been streamlined to accommodate the new calibration measurements. Figure 5 shows an example of some main steps in the data analysis procedure. In this figure, coarse spectral structure and power excesses that do not resemble axions are removed in the individual intermediate frequency spectra, which are then upconverted into radio frequency spectra and combined into a grand spectrum across the whole scanning range by taking an optimally weighted sum of all the rescaled subspectra. The grand spectrum is then used for further analysis. From September 2019 to April 2020, the Haystack experiment has covered from 4.1 to 4.178 GHz. The search rate is enhanced by a factor of 2 as the squeezing setup enabled us to break through the standard quantum limit, and we have excluded the presence of dark matter axion in this mass range. Future experiments will continue to explore ways to further improve the sensitivity in the search for new fundamental particles using quantum technologies. I would like to thank the Haystack collaboration and Professor Maruyama's group for their support in this project. Thank you for listening.